Okay, so welcome to lecture 10 of PYL102. So in this lecture, I will discuss about the lattice vibrations and concept of phonons to understand the certain particular behavior of solids, right? So let me start with this. When we discussed about the specific heat, um, in solids, specific heat of electrons, right? So what we found out that using the equipartition of energy yields result which is given by this C equal to 3 by 2 and Kb, right? So that is temperature independent, right? When we measure a curve like A on the right hand side, right? And this A, as I discussed in the earlier classes, that this can be broken up into two components, right? One is the linear component, which is B, and one is a cubic component in T. The curve is shown as C, right? So these are the two components, and as you have seen from the Sommerfeld's free electron theory, we have figured out that the linear component is due to the electrons, right, which is now gamma T, right? So the other component, which is T cube term in the specific heat, this turns out to be due to phonons, right? So what is phonon? I am coming back to that, right? So this has to do with the lattice vibration, so vibration of all the atoms in the solids. Okay, so there is another point I would like to show here, right? So if you measure the resistivity, for example, of a metal, right? So what you see is that if you keep on measuring the resistivity as a function of temperature, then the data that you get is like this, right? So that means the resistivity increases as a function of temperature, right? So that means there is a certain physics which is working in to define the resistivity as you increase the temperature, right? So what is that that physics? So it turns out that again this temperature dependent increase of resistivity is due to the interaction of electrons with phonons. Okay, so that means it's an important aspect to understand the physics of solids and related electronic behavior. Okay, so let me now show this slide, right, where I'm trying to show the analogy between the electromagnetic wave and acoustic waves. Okay, so now so let us consider this. So if you take a solid, right, so far what we have been discussing is that the atoms are all stationary, right? That means atoms are all fixed, and we have discussed about the free electron behavior and then later the band electron properties, right? So as you remember that in nowhere we have considered any vibration of the lattice, but in reality the atoms which are sitting at each lattice points are not actually stationary. Okay, so at any given temperature they vibrate about the equilibrium position, right? So if you remember your earlier classes, maybe during your school days, right? So if you have two atoms, if you bring them closer, right? So this potential energy is energy has a minimum, right, which is the equilibrium position for the two atoms, right? So now at the equilibrium position, each atoms, we have considered that they are stationary. Now what we are saying is that they are not stationary. We are now considering their vibration and trying to understand their physics, right? So as I said that each atom at each lattice points, they are vibrating with a small amplitude about the equilibrium position. Okay, now this vibration leads to elastic or acoustic waves in solids. Okay, so now in analogy to electromagnetic waves, right? So let me show it here. So electromagnetic waves, right? If you have a certain de Broglie wavelength lambda of an electromagnetic wave, right, then you can define the energy. So you can define the particle aspect, which is the photons, right? Which have quantized energy, which is given by E equal to h nu, right? Where h is Planck's constant and nu is the frequency, right? And the momentum is equal to h cross k, right? Where k is the wave vector, and this is given by 2 pi by lambda, right? So lambda is the de Broglie wavelength for the photons, right? Now, in analogy to electromagnetic waves, in these acoustic waves, which we are discussing for the solids, right? So these acoustic waves, they have a wavelength lambda. I'm saying lambda elastic in this case, right? So if you know lambda elastic, then you can define a wave vector. Here the wave vector, just to distinguish between the wave vector in case of photons photons, and in case of phonons now we are showing it by q, right? In other case it is k. So phonon wave vector ku equal to 2 pi by lambda, which is the wavelength of the acoustic waves, right? So if you know the de Broglie, if you know the de Broglie wavelength, you can find out the wave vector, and your momentum is given by h cross q, right? So these phonons, these phonons are actually the quantized quantum of lattice vibrations, right, which leads to these acoustic waves. Now this quantum of energy of these phonons is given by h cross nu, h nu, right? So that means it's again Planck's constant times the frequency corresponding to that particular wavelength of the acoustic wave. So this is the analogy. So we are in case of electromagnetic waves, we are talking about photons, right? This is the quantized particle corresponding to each wavelength, right? Here in this case, this is phonons, which is again a quantized particle corresponding to that wavelength lambda elastic. So so that means then this lattice vibration, this can be characterized by propagation velocity, right, v, and wavelength lambda, as I've just discussed, or wave vector, right, and frequency or nu, or the angular frequency omega, which is equal to v times velocity times k, right? So this velocity actually is the velocity of sound, right? So in the solid, so which is due to the acoustic waves. So sorry, it should be v times q, okay, not k in this case. Okay, so now what we consider here to understand the lattice vibrations or the phonons. So what we want to do here is actually for electrons, you remember that we have determined the dispersion relation. Similarly, here we are looking at the dispersion relation, where energy versus wave vector, right? So we try to see that how the what is the behavior of the energy or the frequency, right? So energy in terms, you can write in terms of frequency. So what is the behavior with respect to the corresponding wave vector in this case. So what we consider here is that as I said, the atoms is consider that they vibrate with a very small amplitude, and therefore we consider the harmonic oscillations in this case. And then Hooke's law can be used to describe this displacement of the atoms from their mean position, from their equilibrium position, right? So once you use that, then you can produce an equation of motion for the displacement of the atoms, and from there we'll try to see how we can generate a dispersion relation between frequency and wavelength. So typically, here in this case, it is the dispersion relation is written as frequency versus wavelength, but this has the same meaning, right? So energy versus wave vector, or frequency versus wavelength. Okay, so now I have discussed what I've discussed is that the quantized lattice vibrations, they have dual wave particle nature, right? So the particle aspect is called the phonons, right? So there's a quantum of lattice vibrations, and now the transmission of a displacement wave in solids is equivalent to the propagation or movements of phonons. Okay, so phonons which have energy h nu or h cross omega, right? And this particular nature, or these phonons, right, behavior of phonons is important to understand. Different physical observations. For example, the electron scattering, as I have just shown for the metals, right, where the resistivity or resistance increases as a function of temperature, right? So this is due to the electron scattering of the phonons, right? So similarly, if you want to understand the thermal conduction, for example, so that is, if you take a metallic solid, right, with a temperature gradient at the two ends, then you see that the heat transport takes place, right? So to understand this, how the heat transport or the thermal conduction takes place, right, you need to understand the behavior of phonons. Okay, so sorry, yeah. So now to understand that, understand the behavior of phonons. Now first we assume this very simplistic case. This is what we will discuss today. So we take an infinite chain of atoms, right, in one dimension. Okay, so it's basically a one-dimensional linear lattice, and we use a ball spring arrangement. So meaning that, as I said, the atoms vibrate, and we consider that the Hooke's law is valid. So therefore, we consider that each atom is connected by two springs. Okay, and so these vibrations. Now, what we'll consider is along the chain of these atoms, right? So that's a longitudinal vibration, right? But of course, they can vibrate also in the transverse direction, so we'll discuss that later, right? So all these atoms are of equal mass m, right? So these are the assumptions that we are considering. So we are considering a linear lattice of one-dimensional chain of atoms, right, which are connected by spring kind of arrangement. Okay, so remember that we are not discussing any electronic behavior here. We are all concerned with the vibration of this lattice from its equilibrium position. Okay, so in this case we are starting with the longitudinal vibration of this. So now if you consider this linear array, right, so we know that there is a lattice constant. The atoms are separated by the lattice constant, which is a, and now we consider these atoms as rth, r plus 1th, r plus 2th, etc. atoms towards the right side of this rth atom, right, and on the left side, so these are r minus 1, r minus 2, etc. right? And then in the figure below, I show the displacement from the equilibrium position. So, and as you understand, then these are connected by these springs, right? So therefore, we consider that, let's say this displacement of the rth atom is towards right, and displacement of the r minus 1th atom towards right. That's what we are considering. So r plus 1th atom so is a little bit smaller than this, right? So and r plus 2th atom. So this displacement, if you plot the displacement values as a function of distance, you will see that this forms a wave kind of pattern, right? So now you know the displacement which is given by u r minus 1 for the displacement of r minus 1th atom, right? So similarly u r or u r plus 1, etc. for all the displacement of all the atoms, right, which are different in this case. So therefore the relative displacement between rth and r plus 1th atom is given by this a plus u r plus 1 minus u r, right, where a is the lattice constant, right, and ur plus 1 minus ur is the relative displacement that has taken place between these two atoms, right, because of this small vibration about the mean position, right? So therefore the force on the rth atom, right, within this balls and springs model is mu, which is the force constant, times the displacement. So ur plus 1 minus ur minus mu times ur minus ur minus 1. So the rightmost expression, right, mu times ur minus 1 is due to the r minus 1 r minus 1th atom, right? So therefore this net force due to these displacements, so net force on the rth atom is due to the r plus 1th displacement, 1th atoms displacement, and r minus 1th atoms displacement, right? So I hope that you understand that. So again, so what we are considering here in this case is that this displacement is only affected due to the nearest neighbor atoms. Okay, this is important, right? So the nearest neighbors for rth atom is r plus 1th atom and r minus 1th atom on the left, right? And their displacements will exert a force on the rth atom. Rth atom itself is being displaced, so the net force is given by this. So I hope that you understand, right? So this is the relative displacement, which is given by r plus 1 minus ur on the right hand side, and ur minus 1 on the left hand side. Okay, so and mu is the force constant, right? So then you can so once you write this equation, right, so then your equation becomes simpler. Fr equal to mu times ur plus 1 plus ur minus 1 minus 2ur, just the simplification from there, right? So now we consider the displacement of the rth atom as ur equal to this plane wave like expression. Okay, so this transmission due to this displacement, now you see that due to these displacements along the longitudinal direction, so as I said, there is an acoustic wave and which gets transmitted, right, which gets propagated. So now this propagation of a plane wave in x direction that can be represented by this u equal to a times e to the power I kx minus omega t, and so this is the displacement equation, right? So then you can consider dur dt. So you take the derivative, and the second derivative gives you this minus omega square times eur, right? So you know what we are doing, why we are doing is that because we know the force being exerted on this rth atom, right, which we have written here, and now if we know this displacement, right, in the plane wave scenario, then you can determine this, take the derivative, second derivative, and then since you know the mass, right, so this is an acceleration, and if you know since you know the mass, because each atoms are identical, they have identical mass of m, then the force acting on this rth atom is m d2u r dt square, right? So and since d2u dt square is minus omega square ur, so therefore the force on the rth atom is actually given by this, right, minus m omega square r. And so now you can equate these equations which you have written. So this is what on the left side what we are getting is due to the from the displacement wave, right, from the displacement ur, right, and on the right hand side what we are getting is due to the relative displacement, and where mu is, and the mu is the force constant, right? So omega square, from this omega square we can determine, so we are what we find is omega square equal to mu by m times this 2 minus ur by, this is the ratio, ur plus 1 by ur minus 1 by ur, right? So you know what we find here is a relation between the frequency and the displacement, right, of the neighboring atoms of the rth atom, right? Now since we have written in terms of a to the power a into e to the power I q r a, what is r a, right? So this is the x term that we have written, right, as the displacement, right? So you remember, and x equal to r times a, right? This is the rth atom and a is the lattice constant, so therefore x is the r times a here. I forgot to mention earlier, right? So e to the power I into q, which is a wave vector, times ra minus, sorry, it should be omega t, not I omega t, right? I is taken out of the bracket. Okay, so now if you do that, omega square equal to mu by m, 2 minus e to the power I qa minus e to the power minus I qa, right? So now this gives us the relationship between the frequency and the and the wave vector, right? So now if you simplify this equation, then we will find actually the dispersion relation. So meaning that we'll know that at what wave vector what kind of frequency of this phonons, right, which we can expect in this particular lattice, linear lattice, infinite linear lattice, right, with the lattice constant a and wave vector q, right? So if you simplify this, right, so this is 1 minus cos of qa, right, ei qa minus e to the power I minus iqa, sorry, plus e to the power minus iqa. So this is cos qa, right? So this is now 1 minus cos qa, and 2 has been taken out, right? So this is omega square equal to 2 mu by m times 1 minus cos qa, right? So so this is then 1 minus cos qa, so this is 2 sine square qa by 2. So omega is equal to plus minus square root of 4 mu by m sine qa by 2, right? So so we take the positive result because this is what is meaningful, right? So negative result would mean actually that that you have waves propagating towards left and right. Okay, so let us consider omega equal to plus square root of 4 mu by m sine qa by 2. So what you immediately see is that omega relation between omega and q, which is a dispersion relation, right? As I said, the dispersion relation can be written in terms of so for electrons, right, we have written in terms of energy and versus k, which is the wave vector, right? Because there we were interested in the energy bands in this case. There, here we are interested in the frequency of phonons, right? So therefore we are writing it in terms of omega, but energy is h cross omega, right? So that's the same thing. So omega versus q. Now this is the dispersion relation for allowed longitudinal waves in a monatomic chain of lattice, right? So now what you immediately see is that this because of the presence of this sine function, right? So this omega is oscillatory. Okay. So now let us consider this. So q is the wave vector, right? So let's say if qa is pi, right, which is the maximum of omega, which can happen, right, then omega square equal to 4 mu by m, right, and which is the maximum value of the frequency. So therefore this omega square I am writing as omega max square, right? So that means at qa equal to pi or wave vector equal to pi by a, we get the maximum frequency corresponding to that wave vector. The phonons of maximum frequency will be excited. Okay, so now if we plot this this function, it's not a perfectly drawn function, but let me try to show it to make you understand what we mean, right? So this is the dispersion relation that you plot, right? So this is omega versus q, and what you see here is that at, as I said, that q equal to pi by a, you have the maximum omega, right? And then this oscillates, so at q equal to 2 pi by a, right? So that sine becomes sine pi, and which is 0. So you do not have any phonons for this particular value. So two things you can see here is that one is that this omega is linear in the low wave vector regime. So small wave vector. So small wave vector means so I'm showing the linearity by two linear lines from on the both directions, both sides of q equal to 0, right? So it shows that up to certain wavelength or certain q value, the omega versus q is linear. So what does it mean? Q equal to q small, it means actually large wavelength, right? So that means phonons of large wavelength uh, will behave as their frequency will be linearly related to the wave vectors q, right? So that means large wavelength, and so this is the relation between the for the acoustic or the sound waves, right? So omega equal to q times v times q, right? So the v is the velocity, speed of sound, and q, so therefore these are the acoustic waves in this case, right? So and this is linearly related in this case. Okay, so now let me show the other aspect of this, what we get from this curve, right? So frequencies corresponding to modes q and q plus 2n pi by a, these are identical, right? So that's what we see, that are oscillatory, and q so q, any frequency corresponding to frequency corresponding to any value of q, and if the q is shifted by another 2 pi by a, right? So these are the same frequencies. So that means that that's an oscillatory function, and these are identical frequencies for those q values, and therefore so I'm considering, let's say q equal to 2 pi by lambda, right? So therefore now, so this is the wave vector, right? Now for q equal to pi by a, right, lambda is 2a, 2 times the lattice constant, right? So q equal to 2 pi by lambda is the definition between the of the wave vector, right? Relation between the wave vector and the lattice, lambda, which is the wavelength, right? Now for q corresponding to pi a in this case, pi by a in this case, lambda is 2a, right? So that is the wavelength. So that means I'm drawing here lattice points, right? So blue circles, field circles are the lattice points. So I'm showing a and a, there is 2a right here. So that means your lambda, which I show here with the orange line, right? So this shows the wavelength of the lattice vibrational wave, right, or the acoustic wave, corresponding to q equal to pi by a, right? That means when your wave vector is pi by a, your lambda will be like this. Okay, this is the full wavelength which covers 2a. Now let us consider another wave vector. Now let us shift q to q plus 2 pi by a, which I am writing denoting as q dash, right? So this is then 3 pi by a, right? Q dash is 3 pi by a. So your lambda in this case, now if you equate with 2 pi by lambda, which is the definition, so your lambda is 2a by 3. Now in this case, so now what we are doing is I am trying to draw the wavelength of this acoustic wave corresponding to the wave vector, which is q plus 2 pi by a, right? That means I have shifted the wave vector to 2 pi by a. Now what I see here is that if I draw these lines, right, so these what we see here, lambda equal to 2a wavelength and lambda equal to 2a by 3 wavelength, they are perfectly similar, because except those lattice points, at other points there is no atom, so nothing happens there, right? But at the point of the lattice, or at the point of the atoms, at the position of the atoms, the wavelengths are exactly of the same amplitude, right? So same amplitude. Okay, so that means for corresponding to these two wavelengths or these two wave vectors, the lattice behaves as the same way. So that means this range, so that means the behavior of the lattice within this pi by a, at pi by a and at 3 pi by a are similar, right? So therefore we consider that the range which is given by q greater than equal to minus pi by a to less than equal to pi by a, this is the range of wave vectors which covers all independent values of qa. Okay, is it clear hope it is clear to all of you, right? So this is an analogy to the electronic behavior in terms of the when we discussed about the reduced zone scheme. You remember that, right? So there we have discussed about the fast Brillouin zone, and within the fast Brillouin zone, within the reduced zone scheme, the fast Brillouin zone can show all the behavior of the other Brillouin zones. It's very similarly here also. What we see here is that the lattice vibrations for different q values, right, which are separated by 2 pi by a, right, are all these can be all discussed or described by the relationship between omega versus k within the pi by a, minus pi by a to plus pi by a to a region. Okay, so therefore here in this case of lattice vibration, this is what we call it a fast Brillouin zone again in this case. Okay, so the values are pretty similar, but don't get confused. This is the lattice vibration wave vector, and the other case what we have discussed earlier is the electrons wave vector, right, in solids. Okay, so now corresponding to very small values of QA, right, that is, if QA is very much less than 1, then one can write omega equal to omega max, and in this max times sine QA by 2. Now when QA is very small, then sine QA by 2 becomes QA by 2, right? So therefore omega is omega max times QA by 2, and this is then shows the linear relationship, right, between omega frequency and the wave vector, which I just mentioned earlier. So from that we can find out the speed or the velocity of this acoustic wave, right, within the long wavelength range, which is now a times root over mu by m, right, which is the omega max value. Which we get from the omega max value. So therefore, so this v0, this is the velocity of sound or the longitudinal wave, right? And now what we see here is that at q equal to pi by a, both the group velocity and the the group velocity or the phase velocities, if you calculate, these are equal, and the group velocity at q equal to pi by a, right, that is at the zone boundary, right, so the group velocity becomes 0. Within the linear regime, group velocity and the phase velocities are equal. Here at the zone boundary, the group velocity becomes 0, because group velocity is del u del q, which is equal to v0 cos of qa by 2, right? So at the zone boundary, this is q equal to pi by a, right? So this becomes cos pi by 2, and therefore group velocity is 0, right? So group velocity is 0, so that means for corresponding to this particular values, the wave forms a standing wave. Okay, so it's not a progressive wave, this is a standing wave corresponding to this particular wave, the wave vector at the zone boundary. So if you remember, what we see from this dispersion relation is that the wavelength, the frequency is linear in q, right, for very large wavelength range, but when the wavelengths become smaller, right, so this dispersion relation deviates from the linearity, and at the zone boundary it becomes flattened. Okay, so now this is what we actually get by considering very simplistic picture of the one-dimensional lattice, lattice with a lattice constant a, which is an infinite lattice, and all the lattice points are or the atoms have masses, equal mass of m. All right. Of course, you can consider at each lattice points you can. So this is a monovalent atom, right? So this is a monatomic lattice, right? So each lattice points we have only one atom, but you can also have cases where more realistic cases where at each lattice point you have diatomic lattice point, so meaning that two atoms. So in that case you have two atoms of different masses, right? Different types of atoms as basis at each lattice point. So we have to then consider the two masses, separate different masses of the two atoms in that case, and then we have to solve these equations to find out the dispersion relation. So we'll do it in the next class, right? So please go through this, right? So, and this is well described in Kittel's book. Okay, so I've tried to simplify that. All right. Okay, thank you very much. And in case you have any questions, feel free to write to me, or also just send me a mail saying that a discussion session will be necessary. I'll be happy to arrange that. Okay, thank you.